So, Gaurav, just check the chat box if there is some question. Okay, let me check it. No question. So far, no questions. Okay, fine. So, let's start it now. I hope it is visible to everyone. Is my screen visible to everyone? Yeah. So now we are going to start the combinational test generation methods. What are the different methods for combinational test pattern generation? So basically there are four types of methods. First one is from truth table, from Boolean equation, from Boolean difference method, and from the circuit structure. So basically in the morning we figured out that there are four fault simulation techniques. Fault simulation techniques means there is a fault and we are going. Oh, I'm so sorry, it was unmute. So I hope now I am audible to everyone. So good evening, everyone. I'm Dr. Menka Yadav from MNIT Jaipur. We are going to start the next session now. Now, in this session, we are going to discuss the combinational test generation methods. There are four methods. From truth table, we can generate from Boolean equations, from Boolean difference, and from circuit structure. So, why the test generation method is required? Basically, first of all, we will have a fault. For example, let's say this is some circuit. In this, I have this fault over here. I have a fault over here. So this fault I need to simulate. So how I can simulate that fault? That is the fault simulation technique. Now test generation means once I am going to give some input, how I can figure out the test pattern is the faulty value and the fault free value of the output is differing. That is my test pattern generation. So in this, we will be studying test pattern generation. Test pattern generation is the kind of further analysis of the output from the simulation techniques, fault simulation techniques. So you can understand it in this way. So there are four methods. First one is from the truth table, then from Boolean equations, then from Boolean difference, and from circuit structure. We'll take it one by one. The truth table method is the simplest one. We'll just look at the truth table, and by inspection, we will be figuring out whether this particular test pattern is generated or not. So this particular example I have taken for you. In this example, there are four inputs. There is fault at this site. This fault is stuck at 1. So stuck at 1 fault can be represented as 0, 1. 0 can be the true value and 1 can be the faulty value. Okay. It can also be represented in this way. Upside means this is stuck at 1. Downside means it is stuck at 0. And it can also be represented in some books, it is represented as stuck at 0 and SA stuck at 1. So these are the various representations for stuck at 0 and stuck at 1 respectively. If we are using this method, so before slash it is fault free value, the true value, and after this slash this is faulty value. This is faulty value. Now I have to generate the test pattern for this. First of all, I have to activate the fault. So where is the fault? Fault is somewhere in intermediate. So it means it is difficult to control. So what I'm going to do is, I have to make, if this is stuck at 1, my job is to make it 0. My target is to make it 0. If I am not able to make it 0, it means I am not able to activate this fault. So in order to, the first job is to activate the fault. So activating the fault means you are having the set of inputs. Means you will be having the set of inputs. So activating this fault means I need 0. That is the goal. To activate the fault, I have to put the goal that I need a 0 over here. This is OR gate. In OR gate truth table, if you can recall the truth table, there are 4 combinations. I can get 0 in the OR gate only in the first case. All other cases, I'll be having 1 as the output. So it means this is the combination which I can have over here. There is only one combination, and this, both of these inputs are 1. So in order to generate the test pattern, I need all the 4 inputs, right? So what is the next job? Next job is first activating the fault. So it means determining the inputs. So I am not able to find out all the inputs. I have activated this fault, but now the next job is to propagate this fault. So the propagation means we have to bring this fault at the output. Bringing it at the output actually will be determined by the other set of inputs. So other gate is this one. This gate is having 2 inputs, and we will do the back propagation. My job is to take this to further. So what should be the other input? Other input is expected to be non-controlling value. This is AND gate. For AND gate, 1 is the non-controlling value, right? So what I am going to do is, I am going to take the non-controlling value 1, and this non-controlling value 1 is going to give me the backward implication. Backward implication means the AND gate, what should have the input so that I should get the output 1. So this gives me the input set is 1, 1. First of all, I targeted this as 0. Then I did the backward implication. Means what it implies, that what should be the input set. So it implies that 0 0 should be the input set. Now my job is to propagate this fault to the output. So this implies that the other set of inputs of this AND gate must be 1. So now the goal is, this is 1, and I am going to do the backward implication. So this backward implication says that the set of input should be 1 1. So basically the pattern becomes 0 0 1 1. This is the test pattern. Okay, this is the test pattern, and with the help of this we are able to figure out that this is possible to detect this fault. Fine. Yeah, so let us proceed now. This exercise is going to keep in mind what should be the backward implication, what should be the forward uh, propagating the fault at the output, and all these things. So if we want to simplify it, just find its truth table. Okay, so finding its truth table, there will be 16 combinations, total 16 combinations in the fault free circuit, and in the faulty circuit there are only, since this is stuck at 1 fault, so the input over here is 1. So there are only 4 combinations from here, and 1 ended with these 4 combinations is going to give us output corresponding to these 4 input sets. So only 4 combinations will be there. So corresponding all the combinations, we are going to figure out whether the outputs are matching or non-matching. And if they are non-matching, what we will be inferring is that the set of inputs were actually the test vectors. So this is another circuit which is taken for the test generation method from the truth table. So in this circuit, you can see this is AND gate, this is OR gate. This is stuck at 0 fault. Arrow is downside, so you can represent it like this also. Stuck at 0 or SA0, or downside arrow, or 1 by 0. Like that you can make it. So first target was actually from the previous method, first target was to make it 1. and figure out that what was the input set. So the input set for 1 was 1, 1, of course. Now the other target is to figure out that what should be the input set, the third input, if I want to propagate it at the output. So if I want to propagate at the output, this is expected to be 0. The other branch is expected to be non-controlling 0, and this is possible only if I have C is equal to 0. So the test vector is expected to be 1, 1, 0, and I am able to propagate this fault at the output. Now let us consider the truth table based test generation method for the same circuit. So what we did, first of all, write the truth table. There are 3 inputs, so for 3 combinations, there are 8 entries. Now find out what is the function f corresponding to each entry. So this f is nothing but a and b plus a and c. This is the combination, right? So this combination, we will be doing the entry and we will be finding out that this f is 1 only if along with a, either b or c is 1. So along with a means a is expected to be 1, and out of b and c at least 1 is expected to be 1. So these 3 are the entries for which f is 1. Now we have to find out the faulty circuit output. So f alpha says that there is a fault alpha, and this alpha fault is stuck at 0. So we are going to find out f alpha for this, right? So what will be this f alpha? This f alpha is a function because the fault was stuck at 0. So this will have f alpha is equal to a plus c, because this is a from here and this is c from here. Since it was stuck at 0, so 0 plus ac is ac. So f alpha is equal to ac. Now with the help of this, a and c, both of these are expected to be 1, 1, then only the output is expected to be 1. So there are 2 cases. One case is this and another case is this. These are the 2 cases when the output is 1. All other cases, the output is 0. Now just try to match f with f alpha. If you are matching f with f alpha, what is going to happen? This f compared with f alpha is going to give us the same results except this. The sixth combination is not matching. The true value was 1 and faulty value is 0. So it means this is the test vector. If I am going to apply 1, 1, 0, then at the output what I am getting? 0 instead of 1. So it means if output is connected to an LED, so for sure I will be finding that the LED is off instead of making it on, which was expected in the true value. All other cases, faulty and fault-free values are same. So what is the test pattern in out of this? This is the test pattern. 1, 1, 0 is the test pattern. So I hope it is understood well that how the truth table based test generation method works. Any question in this? Yeah, so let us go to the next one. So the next one is the test generation method from the Boolean equation. So Boolean equation or the logical equations, you can generate the test pattern. How you can generate? Just have a look at this truth table. In this truth table, if you look closely, f and f alpha are differing at one place. So if I am having f XOR f alpha, so it means except this value, everywhere I will be having all 0 entries. So can I say that I have to figure out the set of test input vectors where f XOR f alpha is equal to 1. And that's what my test pattern is. Okay. So this thing is taken into Boolean equation. So this is how the Boolean equation works. First of all, f is written in terms of Boolean equation. Then f alpha is written in terms of Boolean equation. Okay. Now t alpha, the set of all tests for fault alpha. How it will be determined? Onset f ended with offset of f alpha plus offset of f own set of F alpha. In other words, you can say that this is F XOR F alpha. So let us find out F XOR F alpha. F was what? AB plus AC. This is AB plus AC. For XOR, we can have the XOR of anything. Let me take it here. I'm so sorry. There is some issue with the device. I hope it will work fine during this 1 hour. Yeah, so F was A, B plus AC. We have to XOR this with F alpha. F alpha was AC. Not able to write very well. Yes. So this is A, B plus AC and this is AC. We have to XOR both of these. So first I will be having AB plus AC into AC whole dash plus AB plus AC whole dash into AC. If I'm going to end this with this, what I'll be having, this is, if I consider this x, this becomes x dash. So this is getting cancelled away. What is left over here, AB ended with AC dash. That is one thing. So first thing, you are left with AB ended with AC dash. So apply the Moore's law, you'll be having A dash plus C dash. A dash ended with AB is going to cancel it away. So you are left with AB plus C dash, right? You are left with this. This is XY whole dash. What you can write it? X dash dot Y dash. So Y dash into, if this is Y, this is Y. So Y dash into Y. So this complete is actually 0. Okay. What you are left with? You are left with AB C dash. What is the meaning of the minterm ABC dash? Please type in the chat box. What is the meaning of ABC dash? 110. Very good. 110 in case of minterms, this becomes 110, right? So 110 is, it means by definition what we were discussing, Boolean difference method T, where T is the set. Yeah, by definition, T alpha is expected to be the set of all tests for fault alpha, where ABC while F XOR F alpha is expected to be 1. So we got ABC dash equal to 1. It means we are left with 110 test set. So this is the test vector. And the way we have generated it is known as the Boolean equation method for the test generation. Now let us come to the next method. Next method is very important and it is Boolean difference method. So Boolean difference method is also similar to the Boolean equation method. In this, what we are going to do is, we have a fault at some point, let's say xi, some branch, we have given some name, xi is the branch name. So we have to find out the Boolean difference by this equation. Boolean difference of any function f, which is a function of capital X, means where x1 to xn are the logical variables. We define df upon dxi is equal to ith variable fi 0. It means we are determining f using x at xi is equal to 0. That is the meaning of this fi0. Likewise, we will determine fi1 by replacing the ith component with ith variable with 1, and then we will take the XOR of both of these, and that is going to give us the Boolean difference. Okay, so now how this Boolean difference is determined and how it is going to work and how it is giving us much more benefit over the past two, let us determine. So in the previous two cases, what we did is we had a fault, right? Then we tried the truth table based fault generation. So in that case, we found that yeah, this stuck at one fault we are able to find out, or whatever fault was there existing, we are able to find out with 110 test pattern, right? In another case also we did the same. So in this Boolean difference method, this is the beauty of Boolean difference method. First of all, we will find out the Boolean difference df upon dxi. With the help of Boolean difference, we will be able to find out the stuck at 0 and stuck at 1 in one go. At that particular branch, we will be able to find out both of the faults altogether if we know the Boolean difference. So this is the beauty of this. There is no need to take the extra steps for the stuck at 0 and stuck at 1 separately. So now let us determine this for this particular circuit. So in this, I have changed the fault site. Fault site is A at the input. Before the branching, it has changed, the fault site has been changed. So we do not know whether this is stuck at 0 or stuck at 1. First of all, we will determine the Boolean difference, and then we'll find out both of the sets, whether it is stuck at 0 or stuck at 1. And those sets will be working accordingly, whatever is stuck at 0 is there or 1 is there. So F was AB plus AB plus AC. Now, if I want to find out Boolean difference, the fault is at input A. So F df upon dA can be written as, first I have to find out F A is equal to 0. So making F A is equal to 0 makes F 0. This is complete 0. So I'm going to make it 0. XOR with make F is equal to 1. So you are having B plus C. A is equal to 1 in this equation gives us B plus C. What is the meaning of this? 0 XOR with anything. What you will have? 0 XOR with anything. You will have anything, right? So 0 XOR with B plus C, what you will be having? B plus C. Okay. So that's what you are having, B plus C as the Boolean difference. Now you have the Boolean difference. Now what you have to do? You have to find out what is the stuck at 0 fault test pattern and what is stuck at 1 fault test pattern. So for that, what you have to do, just find out the set of all vectors where stuck at 4 is stuck at 1. Stuck at 1 means we just need to take 0 for that. To activate that fault, I need a 0. Or 0 in case of min terms, 0 implies what? Complement value. So if the fault was at A, so 0 means it is A dash. So I'm going to apply A dash df upon dA is equal to 1. So this test set of input test vectors is equal to my test for stuck at 1 fault. Likewise, for stuck at 0, what if this was stuck at 0, my job is to make it push it to 1, and 1 for min terms. 1 means the prime value A. So I'm going to AND this df upon df by dA with A, and that is equal to 1. That is going to give me the set of these test vectors. Okay, I hope you got it. So In this fashion, you can find out your set of input test vectors. So in order to make it a little bit more clear, let me elaborate it, how you can find out these test vectors. So the simple df upon dA, we got B plus C, right? We got B plus C. Now, by definition, stack at one fold, I want to find out. It means I need to push A to, the fault is here. Please remember, the fault is not here now. The fault is at the input. So I want a stack at one fault pattern. So it means A is expected to push to 0. So 0 is equivalent to A dash. In terms of min terms, this is equivalent to A dash. So I will be having the sets which are df upon dA is equal to 1. So it means it is A dash B plus C is equal to 1. Find out how many minterms are there. A dash means A is 0. B plus C. B plus C represents what? Either B or C is, either B is 1 or C is 1. So can I write it in this way? That 1 x comma 0 x 1. You got my point or not? X means if C is 0 or 1, I don't care because B was 1. And this X means B is expected to be anything if C is equal to 1. And this gives me 1. So basically these are three minterms. 0, 1, 1, 0, 1, 0 and 0, 0, 1. These are the three minterms I will be having in this case. I hope you got it. Likewise, we can take it for stack at 0 also. So if you want to take it for stack at 0, what you have to do? Make it stack at 0 means your job is to make A is equal to 1. A is equal to 1 means it is the prime. So just add this with the Boolean difference d by dA and it's going to give you A B plus C. What does it mean? It means, and that is equal to 1. So this set of all these patterns is actually your test vector for stack at fault 0 at A. A is 1 here. B or C, either one of these is expected to be 1. So these are the test vectors for A stack at 0. Okay. So these are the three things: 1, 1, 0, 1, 0, 1, and 1, 1, 1. Three patterns. Because 1, 1, 1 is common in both of these, right? So these are not false. X means it can take two values. For example, if I discuss this is equal to 1, 1, 0 and 1, 1, 1. Likewise, if we take this, then this is 1, 0, 1 or this. Okay. So since this the second combination is common to both of these, so we'll cut any one of this. So there are three combinations, 1, 2, and 3. And likewise, we will find out. Okay. So now let us consider the example that instead of the fault at site A, let us have the fault over here. This is the fault, and in order to deal with this, how to start? So look at this fault is there, not at the inputs. So if it is not at the inputs, first of all, make sure that you are going to give the name to each and every gate and each and every branch. So give the name to all of these. Let's say this is G1, G2, G3, like that. And let's say this is H, this is I. Okay, any name you can give. Now instead of df upon dx, what I need I need df upon dh, but h is not the input. So first of all, I need to write h is equal to ab. That is the thing. And f I have to write in terms of h. H is not the primary input, but still, since I have to create the Boolean difference, so this is how I can write it. Now I can figure out df upon dh. df upon dh, the Boolean difference. So the same thing, h is equal to 0 is going to give me AC, XOR with h is equal to 1, that's going to give me A. It's going to give me A plus C whole dash, right? This is what I am getting. Okay. Now, according to the Boolean difference, if I have a fault h, let me write instead of this, let me write h stuck at 0. So for h stuck at 0, what you need? You need h is equal to 1. H is equal to 1 means the prime, it will come. So the test set will be h df upon dh is equal to 1. All vectors related to that will be the test pattern for stuck at h stuck at 0. Okay. So h was AB, will revert back to AB. Why? Because we only know the input, we need to create the input patterns. So h was the intermediate input, so we will convert it back. Once the processing is done, we have to convert it back. So we will replace it with AB, h was AB, and this was ended with A bar, C bar, A bar plus C bar. So what you are left with? You are left with A, B, C bar. That is nothing but 1, 1, 0. So H stuck at 0, this combination we have studied earlier also. What was the combination? 1, 1, 0 was the combination to test this fault. Okay. Now what about if it was H stuck at 1? If it was the case, then that case we will just make H dash DH df upon dh, right? So let me change the pen. So we will just change in this way. So it means A, B whole dash along with this. So if we are going to make it in this way, let me write it in on next page. It becomes A, B whole dash A bar plus C bar, which was already over there, right? So we are left with A bar plus B bar ended with A bar plus C bar. What we can write? We can write A bar plus B bar C bar. So for H stuck at 0, we got 1, 1, 0 as the test vector. For H stuck at 1, we'll have this as the test vector. Yeah. So this is the test vector for H stuck at 1. What is this test vector? So this is a combination of 4 things. What are those 4? This is, we have reduced 2 variables to get this literal, right? So this is actually nothing but 0 x x comma. What is this? This is nothing but x b bar and c bar 0 0 x b. So these are the total combinations. These are 4 combinations. So this contains 0 1 2 3, and this is actually 0 and 1 0 0. So 4 from here and 1 from here. 1 plus 1 it will be from here, but all zeros we will omit. So there are total 5 combinations. So if h was stuck at 0, this was stuck at 0, I am having 5 combinations starting from 0, 1, 2, 3 and 4. These are the combinations I can have as to detect this fault using the Boolean difference method. So the Boolean difference method is the one which is going to give us the flexibility to get the stuck at 0 and stuck at 1 fault altogether. Okay. Fine. So Boolean difference method we have discussed. Yeah, this method we have discussed. Now, how to generate the test pattern from the circuit structure. So in order to generate the test vector from the circuit structure, I have discussed earlier what we have to do. First of all, we have to go for the fault activation. This is the fault activation. Then we have to do the fault propagation. So basically, fault activation means the goal is to bring just opposite to that value whatever we are having the stuck at fault. So let's say this is stuck at 0. So if this is stuck at 0, then what is our goal? Our goal is to bring it 1. Bringing 1 means I need both of the inputs as 1. Okay. So this is the fault activation. First we will do that. Once the fault is activated, so it means I have 1, 0. 1 was the true value, 0 is the faulty value. Now my job is the fault propagation. So in order to propagate the fault, my job is to push this fault. Propagate means push this fault at the output. So for that, what I need to put non-controlling value at the other edge. So non-controlling value is 0 in this case. It is OR gate, right? So for OR gate, non-controlling value is 0, right? So in order to get 0, I have only one. I have 3 combinations. For AND gate, I have 3 combinations: 0, 0, 0, 1, and 1, 0. But here, it is fixed because A was 1. So if A is 1, the only thing is remaining 0. I have to make it 0, and my test vector becomes 1, 1, 0, right? And in this manner, I am getting 1, 1, 0 as the test vector. This is from the circuit structure. Now, basically, let us call this 1, 0 and 0, 1. Again and again, talking about 1, 0, 0, 1 and all. This is problematic. So we are going to give it a name. Let us give it a name D. D means if the true value is 1 and the faulty value is 0, we are going to denote it by D. Means the true value was expected to be 1, but faulty value is 0. D dash means D dash, just opposite of this. So D dash is the faulty value is 0 and the true value is 1. We are going to denote it by D dash. Okay. So D and D dash are called as fault effects. So there are some common concepts for structural test pattern generation. First of all, fault activation problem. So this fault activation problem is, our goal is to activate that fault and find out the corresponding inputs. So this is the line justification problem, that which line the fault is going to exist. Depending on that, corresponding those inputs, we will be backtracing and we will be finding out the input set. Then there is another problem is the fault propagation problem. So select the fault propagation path to the primary outputs. PO is the primary output. So it is the decision, what decision you are going to take. This circuit was smaller circuit, so we couldn't take that much of multiple paths. So if there are multiple paths, we have to take the decision that through which we want to propagate this fault to the primary output if multiple paths are available. Once the path is selected, it becomes the problem of line justification. Again, line justification means you have to do the implications, that what is the output corresponding those output, you have to backtrace and you have to find out what was the input. For example, in this particular case, if C is 1, it means what is expected at the A and B? It is AND gate, so we are expecting 1, 1. But if C was 0, so in that case, we have to make a decision. Either A was 0 or B was 0, or both of these can be 0. So there are 3 possibilities: 0, 1, 1, 0, 1, 0, 0. So out of these, we have to make the decision. That decision should be suitable to us. For example, in the previous case, out of 3 conditions, we have taken 1, 0. Because A was already fixed to 1. That's what we made C is equal to 0. So that type of decision we have to take. This is what the line justification problem is. But if the decision is not correct, then we have to backtrace again and we have to take another decision if it is available. If we have backtraced completely and we are not able to find out the correct decision, then we will say that this particular fault we are not able to detect. Such type of faults are called non-detectable faults. Okay. So this is the decision when fault propagation is done. With the help of this example, let us understand. There are multiple branches at different places. So that is going to impact the things, right? So F1, F2 are the two outputs. Our job is, first of all, let us have the fault. You can see over here, every gate has been given some input, name. Likewise, we have to give the name to every branch, every stem, every branch, every line, we have to give some name. Okay, so inputs and outputs are given some name. These intermediates also need to give some name. Okay, now first of all, the first thing was the fault activation. So in order to activate this fault, this is stacket 1. If this is 1, what should be the input set? What can be the input set if this is 1? This is NOR gate, NAND gate. NAND gate output 1. When is it possible? There are multiple combinations. How many combinations are possible? This is a 3-input NAND gate. So all of these inputs are 0, 0, 0. Output is expected to be 1. 0, 0, 1. Output is expected to be 1. And likewise. Okay. Now, okay, out of those sets, let's say I got this set. I figured out, okay, I will go with this set. So this set, actually, I have taken all zeros. So 0, 0, and 0 I have taken. Now I have to propagate this fault maybe through this or through this. So I have to take one justification. Let's say I want to propagate this through G5. Okay, I want to propagate it through G5. Oh, I'm so sorry. It is stuck at 1 fault, so I have to make it to 0. This is stuck at 1 fault, so I have to make the NAND gate output to 0. So the 0 output for NAND gate, there is only one combination. All of the inputs are expected to be 1, 1, 1. All of the inputs are expected to be 1, 1, 1 for the fault. And these two are rings. So now we are going to take the decision. These are 1, 1, 1 fault activation. Now next one is to propagate this fault through this. Let's take the decision. We want to propagate it through G5. So if we want to propagate it through G5, it means what? This should have the non-controlling. Non-controlling means what? What I should have over here? AND gate non-controlling. Yes, please type in the chat box. What should I have for the non-controlling value? So I should have 1, right? 0 is the controlling value. It controls irrespective of any other value. 0 is going to give AND gate 0 only. 1 is correct. Thank you, Dr. Aditya. 1 is the controlling value. So non-controlling value. So non-controlling value is 1, and the fault we are able to propagate through this. So this was stuck at 1 fault. It means I can write it. True value is 0, faulty value is 1. So I can write it D dash. So D dash ended with 1. I'm getting what I'm getting at the output. So I can get it D dash. Okay. Yeah, that's correct. But now there is a problem. This one, how I can get? I have to backtrace. So backtracing this, I will find that I cannot get this as 1. Why I cannot get? Because this is NOR gate. For NOR gate, there is only one combination, and that combination says that A is equal to 0 and D is equal to 0. A was already fixed in the fault activation, so I cannot make that 0, but I was free with D. So it means there is inconsistency. So we cannot go with this decision. So I cannot go with this path. It means I have to change my path. So let's change the path and try to propagate it through this. So propagating through this, Same thing, we'll backtrace it and we need 1 at the output of G4. G4 is again NOR gate and the output of this is 1 if I can have 0 over here and 0 over here. So can I have 0 at both of the places? Yes, I can have. E is equal to 0 I can have, first thing. And C was already 1, so the output of this inverter is 0. So basically, I am okay with E is equal to 0 and then my job is done. So basically, this is the path and we have done. So basically, these three inputs A, B, C were for the fault activation and this fifth one E is equal to 0 is for fault propagation to F2. So we are able to detect this fault. Now what is the test vector? In test vector we have to include D also. So we do not care about D because for this path D doesn't matter, right? For path from G1 to F2, it doesn't matter that what was D. So D is don't care. So it means we have two patterns for this particular thing. One is 1 1 1 1 0 and 1 1 1 0 0. These are the two test patterns I can have for this particular problem. So I hope you got how to make the decisions and how to find out that what was the test pattern from the circuit structure. So this is the another problem. It is first problem we have taken earlier. Now this is the similar problem. So in this, the fault is stuck at 1 at H. I have to activate this fault and then I have to propagate. So propagating this fault is there is only one path. This is the path. Okay. Activation also it requires E, F and H. First of all, this is stuck at 1. So it means I have to put H is equal to 0. So H is equal to 0. And it was stuck at 1. So I can write it D dash. H I can write D dash. Okay. What other should be E and F? These should have the non-controlling value. So non-controlling value is 1. So 1, 1 and 0 is the input E, F, H. But there are other inputs we need to determine. Then only the complete set we can determine and we can make sure that whether we are able to propagate this fault at the output or not. Okay. So for this fault we are able, look, this is D dash, right? D dash ended with 1, ended with 1. What I am getting over here, D dash. Now this D dash can be pushed to the output in form of D dash only if I have Q is equal to 1 and R is equal to 1. So now Q is equal to 1. There are multiple combinations for Q is equal to 1. This is OR gate and this is also the output of OR gate. So for this there are three combinations. K can be 0, L can be 1. K can be 1, L can be 0. Both of these can be 1. Likewise, there are three combinations for this as well. M, N and O. There are these three combinations are there. So there are 7 combinations in total. 2 raised to power 3 minus 1, 7 combinations to get it 1. So out of these, which combination we should select? First of all, we have to take the decision that we will go with this and then we have to proceed. So first of all, let us start with taking the decision. Okay, let's take the decision L is equal to 0. Let's take the decision L is equal to 0. So if I want L is equal to 0, it means either C or D is expected to be 0 or both of these are expected to be 0. So if that is the case, then R is coming 1. You can see from here, if C or D, any one of these is 0, then R is coming 1, right? Because from E, we are not able to get 1 at the output. So we have to maintain either C or D is equal to 0. And we are getting output R is equal to 1. Now A or B, A and B we can put 1 1 and our job is done. Okay. So my test pattern can be 1 1 0 X 1 1 0, or I can make D as 0. So this can be the test pattern. Okay, and my job is done. If I would have taken the decision L is equal to 1, in that case, L is equal to 1 means I have to make sure C and D, both of these are 1, 1. That is going to lead always R is equal to 0. So that we will find inconsistent. So it means we have to backtrace and we have to find out it again. So in this way, we have to make the decisions and then we have to find out. So on paper and pen, it is okay to complete because this is very small circuit. But when we are talking about the real-time circuits, those are very complex. So it means we have to uh, run some algorithm that can help us to find out the test patterns for each and every fold. So there are different algorithms, and yeah, one such algorithm is D algorithm. So I'm skipping the implications. We have already done the implications. So local and global implications are the things. Local implication means just before or after that, what I should get. Global means, let's say at some other branch, you have something and how it is going to impact at the input or output. That is the local and global implication. Okay, so yeah, let us have a look at D algorithm. I want to complete this D algorithm because tomorrow sir is going to take something related to sequential circuit testing, so it can be useful for you. What is D algorithm? In D algorithm, we will be dealing with 5 values instead of 2 values, 0 and 1. One is 0, another one is 1, which are normally binary logic values. X is the don't care. D means the true value was 1 and the faulty value was 0. D dash means the true value is 0 and faulty value is 1. Okay, these are the things. So these are the 5 values. So there will be a 5 cross 5 matrix. And how this 5 cross 5 matrix will work, let me take it over here, how it can work. So there will be 5 values. For example, I am talking about AND gate, AND operation, OR operation, NAND operation, whatever operation you have. So you have input A over here, B here. So it is 0. 0 can be written as 0 as the true value and faulty value is also 0. 1 can be written as 1, 1. D can be written as 1, 0. D dash can be written as 0, 1. X can be written as true is also X, faulty is also X, like that. Likewise, it is 0, 0, that is 0. 1, 1, that is 1. 1, 0, that is nothing but D. And 0, 1, that is D dash. And this is XX. So 0 ended with 0 is going to give me 0. 0 ended with anything because 0 is the controlling value. So likewise, I will be having 0. 1 ended with anything is the same value, right? 1, D, D dash, X. And likewise, this is 1 ended with anything is going to give me the anything. Now it comes to this. This was D, D dash, and like that. So D ended with D. What I should have? When I am going to AND both of these, true value is ANDed with the true value. So 1 is ANDed with 1. And faulty value is ANDed with faulty value. So 0 is ANDed with 0. So I am getting 1, 0. D is ANDed with D dash. So 1 is ANDed with 0. That is going to give me 0. And 0 is ANDed with 1. That is again going to give me 0. You got my point? So what I'm having over here, I'm having 0, 0. And likewise, D ended with D dash also, I'm getting 0, 0. And D dash ended with D dash, I'm getting again D dash. X ended with X, I'm getting X. And D ended with X. So I will be getting 1 ended with XX slash 0. Okay, we can denote it by X. We can denote it by X. So this is the simple logical operation for 5 value system. 5 value means you have one value 0, 1, D, D dash, and this is X. Okay. Likewise, if it is OR gate, then D plus D is D, but d plus d dash. So d plus d dash means you can make it like 1 0 was there and then 0 1. OR gate we are talking about. So 1 plus 0 is 1. 0 plus 1 is also 1. So what you should have? You should have 1. This entry will become in OR gate. These entries will become 1 1. Okay, true value 1. So that is how the OR gate can be implemented. Okay. Now keeping those things in mind, let us consider this case. This is an example. Here A is stuck at 1. A is stuck at 1 after the branching. After the fan out, it is stuck at 1. So if this is stuck at 1, how I can activate that? First of all, I have to activate this. So it means I need to make A is equal to 0 so that I can activate this. So A is equal to 0 I have taken. Now next I have to make other two inputs B and C non-controlling. So since this is NAND gate, so the non-controlling for NAND and AND, both of these are same 1 1. So ABC I will be having 0 1 1. Okay, got my point? Now the fault is here at this line. So it means this is the gate through which it can propagate. If this was 0 and the fault was 1, so I can write it D dash. D dash ended with 1, ended with 1. And then end of that, what I'll be having? D dash and dash of that. That is going to give me D. You got my point? So the output of this becomes D, right? Output of at G, I'm having D. Now this D, there are three paths to propagate. You can take this path, or you can take this path, or you can take this path. There are three paths. Out of those three, you can take any one of those paths. Now, if you are taking, first of all, let's choose one by one. Let's say I want to take I path. For this, I want to take I path. So this I path, it means all other than I. Those should be 1. Why those should be 1? Because those are the non-controlling values for the last gate, NAND gate, right? So this is through this I want to propagate the fault through this. So it means I am expecting this is expected to be 1, this is expected to be 1, this is expected to be 1, 1 and 1. Then only I can propagate it through I. Okay. So for I, if I want to propagate it through this, what I should have at D? I want to propagate it through I. So D is expected to be non-controlling. And what is the non-controlling? Non-controlling is 1. So if this is 1, I'm going to make it 0. D dash becomes 0. So this 1 and 0, 0 ended with anything, I am getting 1 at the output. That is true. That is good. So it means, yes, D is equal to 1 is going to give me, okay, I can propagate the fault through this. But now we have to check for J, K, L, M. So let's check for J. So checking with J, my target is to make J is equal to 1. So how I can make J is equal to 1? Just have a look at this. This is coming from B. B is already 1. This is NAND gate. So NAND gate, when I can have it 1, there are 3 combinations 0, 0, 0, 1, 1, 0. So out of those, I can only choose 1, 0 because other one is already fixed during the fault activation. So if I am going to make it 0, what is the backward implication? E is equal to 1. This E is equal to 1 along with the D, this which is D, what it is going to make it? D dash. Okay. It is not going to make it 1, but it is, instead of that, it is going to make it D dash. So D dash, here it is D dash and here also it was, oh, there is something wrong. Yeah, it was 1. So it was D dash. At I also it was D dash. And here also instead of 1, I am getting D dash. So D dash ended with D dash is D dash only. So it means I can simultaneously propagate the fault through I and K, not alone with I. Now my target is to make this is equal to 1 and this is equal to 1. So now let us proceed. So first goal is to get L is equal to 1. Back propagate. So C was already 1. I can play with F. F dash is expected to be 0, so that I can have 1 over here. Backtracking this means F is equal to 1. And then this 1 means, look at this, this was again D. So 1 over here, D ended with 1 means it is D dash. Okay, at M also I am getting D dash. But yes, if F is equal to 1, I can get here L is equal to 1. Okay, and with the help of this, I can figure out that I can propagate. There is only one way to propagate this fault, and that way is to have, what is that way? The way is to propagate the fault all together with these three. Okay, I can propagate the fault with these three. That is the only option. There is no other option, because if I am making it 0, let's say, so this is going to make it 1, of course, but at the same time it is going to, this is going to make it 1, and 1 and 1 it is going to make it 0. So irrespective of any other input available to this last gate, it is going to make it 1. Output becomes, NAND gate becomes 1, because 0 becomes controlling. So I cannot afford that. So it means I have to keep it 1, I have to keep it 1, and this I don't care, because this was already 0, A was already 0, and because of that this H is already 1. So I really don't care about that. Okay, so what is the test pattern? Test pattern becomes 0, 1, 1, and D is don't care. If it is 0, then also it's okay. If it is 1, then also it's okay. Okay, why it's okay? Because if it is 0, then irrespective of anything, I'll be having the output over here as 1. So it means I am not able to propagate the fault through I, but yes, I can choose either K or M path. If this was 1, then I have the flexibility to take the fault propagation through I, J, I, K, and M. These three. So next is 0, 1, 1, 0, X, 1, 1. This is the test pattern. So this is the combination circuit ATPC algorithm test pattern generation method. And this type of algorithms, you can write the program in your any of the language, and then it can automate. It can be automated. So with this, let me conclude this session. Gaurav.
Yes, ma'am.
So is Mr. Harsal is with us?
Yes, ma'am. So actually means yes, ma'am.
Just check in the other attendees list if he is there. By that time, others can ask the question, and you please switch the session.
Okay,
Please
ma'am.
switch the session.
Let me make him a
Others-
panelist first, ma'am.
Yeah, we have to make him panelist.
Yes, ma'am. Okay. So shall I quit the session, ma'am? And we can continue after 5 minutes and continue the session, ma'am. Hello, Harshit sir.
Yes, let's take a 5 minutes break to switch the session, then we will start.
Okay.
So, good evening, Mr. Harsha Jaiswal.
Yeah, hello, good evening,
so
madam.
much. Yeah, so we will start in 5 minutes, sir.
Sure, I wait.